Okay, so once you get used to drawing your Lewis diagrams and you understand there can be a double bond, there can be a triple bond, we're going to talk about a new category of molecule because this comes up pretty often. This is a very common thing. This new category is what we call an oxoacid. And an oxoacid is when you have a compound made up of, oh, it's right here, compound made up of a nonmetal, hydrogen, and oxygen. Okay? The hydrogens must be attached to the oxygen in this compound. Also, the oxygens outnumber the hydrogens. So in other words, in order to be an oxoacid, example, HNO3, that is an oxoacid. It's made up of a nonmetal, hydrogens, and oxygens, and the oxygens outnumber the hydrogens. There's more oxygens than hydrogens. Okay, here's an example of something that looks like an oxoacid but is not. Do you guys see the difference? You have a nonmetal, you have oxygens, and you have hydrogens. So it meets the first rule, but it doesn't meet the second rule, which says the oxygens must outnumber the hydrogens. There's more hydrogens than oxygens. This is not an oxoacid. So, first thing, you have to be able to identify an oxoacid when you see it. These three here are all examples of oxoacids. Okay, now whenever you are drawing a Lewis diagram for an oxoacid, the hydrogen is attached to the oxygen, not the center. So watch. For this first example, hydrogen has 1 valence electron, chlorine has 7, and there's 3 oxygens. Okay, so 8 plus 18 is 26. Chlorine in the center, oxygen, oxygen, oxygen. Now, your initial thought might be to put the hydrogen here, right? Because that would kind of make it look symmetrical. But here's where you have to understand that this category of compounds does not have the hydrogen on the center. The hydrogen must be attached to one of the oxygens. It doesn't matter which one, it just can't be on the center. Okay, so we go about drawing the diagram like we would have. We've got 26 electrons to work with. You do the outside atoms first. Okay, so far, if I count these up, I've got a group of 8, a group of 8, and a group of 8, so that's 24. I have 2 more electrons to place, and they go on the center. And now I'm done with that guy. Okay, let's try the next one. Okay, so let's add this up. Hydrogen has 1, but there's 2 of them. Sulfur has 6. Oxygen has 6, but there's 4 of them. Okay, so 2 plus 6, that's 8. 8 and 24 is 32. All right. Sulfur in the middle. I got 4 oxygens, so that makes it easy, just 1 on each side. There are 2 hydrogens. Pick 2 oxygens. It doesn't matter which ones. And finish the electron placement. And that's 32. And now we're done. Take a minute and try C on your own. Okay, I'm going to start drawing. Okay, so hopefully you have something similar to mine. It doesn't matter if you picked the same placement of hydrogens as long as they're only attached to O's. Okay, so you guys okay with oxoacids? Right, you know how to recognize one if you see one. Okay, it has to be more oxygens than hydrogens. Okay, all right. Resonance. So sometimes you'll draw a Lewis diagram, and the Lewis diagram, even though it looks good on paper, might not be how it experimentally is determined. So an example of that happens when you have double bonds. So for example, or multiple double bonds. So for example, SO3. If I were to draw SO3, this would give me 24 electrons. There's only three oxygens, so I'm just going to place them around like that. And once I get my electrons placed, I realize, okay, I've used 24 electrons right now, 3 groups of 8, but my sulfur does not have an octet. So that means this is wrong. So what you've learned by now is how to fix that, right? How do we fix this? Yeah, we're going to need a double bond somewhere. So I'm just going to pick an oxygen, just going to pick that guy here, and rewrite the electrons as a double bond. Okay. So here's the thing, though. This drawing, this Lewis diagram, shows a double bond, and it shows 2 single bonds. Now, the thing is, double bonds and single bonds are not the same length. Right? A double bond, and I'm going to zoom back to our notes, something we haven't covered yet. We kind of skipped over it. I'm going to, where it says bond length. Here we go. So a single bond, you share 1 pair of electrons. A double bond, you share 2 pairs of electrons. A triple bond, you share 3 pairs. So that makes sense because you've now drawn a couple of examples, right? And the bond length is the distance between the nuclei of the atoms. But the thing is this. Double bonds are shorter than single bonds. So a triple bond is the shortest. And if you think about this, this makes sense because when you have more electrons attracting atoms together, it pulls them in closer. All right, so for example, here's a single bond. In a single bond, you have 2 electrons that attract the nuclei. Okay. In a double bond, you've got 4 electrons attracting the nuclei. So, double bond, greater attraction equals shorter length. And of course, if we have a triple bond, you have the greatest attraction, and now you have the shortest bond length. Okay, so are you guys okay with that? Double bond shorter, triple bond shortest. You guys okay with that? Okay, so let's jump back to where we were. Okay, so here, our diagram shows one double bond and two single bonds. Okay, but in reality, the molecule has 3 equal length bonds. So that means the drawing that we have is not right, because a double bond and 2 single bonds, they look like different bonds. And if they're different bonds, they would be different lengths. Okay, but the magnetic testing has shown that in this molecule, all bond lengths are the same. So what that means is that this Lewis diagram does not adequately show the molecule in reality is actually an average of different structures. So I'm going to draw this molecule 2 more times. So do you see how the difference between the first molecule and the second molecule? Effectively, it's the same, but what's different? The double bond is now in a different place, okay? And I'm going to do this one more time. So that the double bond is shown in 3 different positions. And what this is meant, what we're doing right here is called resonance. And resonance is meant to show that the bonds are actually averaged. Okay, so the real structure is an average of the 3. Neither one on its own is correct. All three are drawn because realistically you have an average of those 3. It's a kind of a weird phenomenon, and the reason why we have to do this is because there's other bonding theories that explain this concept of resonance better, but we're not going to teach you in another entire bond theory because you need much, much more time. Okay, so how do we know when you have to do resonance, when we have to show this multiple Lewis structure? You have to do this whenever a double bond is drawn in a place, but it could have also been drawn somewhere else. So this molecule has 3 oxygens. I arbitrarily picked this oxygen to double bond it. But if I could have picked a different oxygen, that means there was more possible places for the double bond to be. And if there's more places for the double bond to be, that means the real structure is an average of all of those possibilities. Let me show you. Here, I'm going to add a page here just so we can do a couple more examples. Okay, so this one here, NO3, okay? So 5 plus 3 times, plus 3 times 6 plus 1. This is also going to be equal to 24. So my first drawing of 24, or of the NO3, would look like this. Okay, that's my first one. Are all of the atoms attached to nitrogen the same? Meaning, are they the same element? They're all oxygens, right? So the fact that I put the double bond on the one on the bottom means I could have also picked the one on the top left, which means the double bond is potentially there as well. And there's also the oxygen on the top right, and that also is where the double bond could have been drawn. So all 3 of these are viable. This molecule has resonance because no one single structure adequately describes it. Okay, Here's another example where we might see resonance. A molecule like SO2. 6 plus 2 times 6. Okay, so now we've got 18. Sulfur in the middle. Are both atoms that are bonded to sulfur the same? Yeah, okay. So let's try to draw our diagram here. So right now I know I have to use 18 electrons, and right now I am showing you 18, but this molecule is incorrect. We don't have enough electrons to fill octets. That means we have to double bond something. So I'm just going to erase a pair and just redraw it as a line. I picked the oxygen on the left, but I very well could have picked the one on the left. Wait, other side, other left. So if that happens, that means you draw it twice. Yes, only if you want full credit. Because you have to show that you understand that resonance is occurring. Is this making sense? Okay. Here, let me show you, and just to kind of drive the point home, let me show you some examples where resonance does not happen. Okay, to kind of clear the, yeah, Chris, question?
Well, for every equation that has the double bond, from now on, we have to draw.
Well, that's what I'm going to show you, because there's some times where it can't. Okay, so here, watch. You just drew this in your notes a few minutes ago. There's a double bond there, right? How many other places could that double bond be? Nowhere. So that won't have resonance. Okay, here's another example. Okay, carbon dioxide, CO2. So 4 plus 2 times 6. Okay, so 8, or 12 plus 4 is 16. Carbon in the center. As it turns out, this molecule is going to need 2 double bonds. So I have 2 double bonds, and the double bonds are already placed. Is there another place I could put a double bond? No, it's kind of set. It's fixed already. So there's no resonance here either. Okay, one more example. HCN, so 1 plus 4 plus 5. So we've got 10. Remember how you decide what element goes into center when there's 3 elements? Yeah, Mackenzie?
Isn't it like the lowest ionization energy?
Electronegativity, yes, good. Lowest electronegativity. So hydrogen can't be in the center, and between carbon and nitrogen, carbon has the lowest electronegativity, so carbon's in the center. I've only got 10 electrons to work with. We've seen this before. 10 is not going to be enough to spread out 8 over everything, right? So that means we have a triple bond. Okay, so there's a triple bond on one side, and there's a single bond with hydrogen on the other side. Can I draw that triple bond on the other side? No. Why? Hydrogen is too small. Hydrogen can only make one bond. So resonance is not possible here. Are you guys getting to see the idea of when a resonance can or cannot happen? Okay. Okay. Actually, let's just do one more, because this is something you might see. And because we talked about oxoacids. HCO3 minus. Okay, so 1 plus 4 plus 3 times 6 plus 1, 24. All right, so carbon in the center, 3 oxygens. Where does the hydrogen go? Does the hydrogen go on top of the carbon? No, it's an oxo acid, so it must go on one of the O's. All right, so let's continue on. Fill up your octets. I've just placed 24 electrons, and that's how many I had. Yet carbon does not have an octet, so by now you guys know this needs to what? double bond. So I'm just going to put a double bond here. Okay, so let me ask you one question. Are the oxygens that are on carbon all identical? No, there is clearly something different about the one that has H attached. Do you see that? Okay. Could the double bond be with the oxygen on the bottom? Yes, it could. Guess what? Resonance. But how many structures? 2. Good. Only 2, because the third one is different, and the third one will not behave the same way as the others. So your other Lewis diagram looks like this. Only 2 that time. The hydrogen here, right, off to this guy, or this oxygen right here that's carrying the hydrogen, he's like, I ain't got time to double bond. I'm busy holding on to hydrogen here. So you guys do your own thing, right? I'm busy. Don't bother me. And so they're like, okay, well, it looks like we'll just resonate, 2 of us. That's cool. Okay. All right. That is the concept of resonance. Yes?
Do you have to draw brackets around your resonance?
You only draw brackets around when? Ions, if there's a charge. Okay. All right. That is where we'll end today.